Imagine a team of software engineers spending 6 entire months painstakingly translating a million lines of 20-year-old banking code.
Oh man, the absolute nightmare of legacy tech debt,
Right. I mean, they are burning through overtime, staring at this archaic syntax and just desperately hoping they don't accidentally break the core financial ledger.
which happens more than people think.
Exactly. Now, I want you to imagine a machine analyzing that exact same sprawling, tangled architecture. It understands every single dependency and it flawlessly generates the modernized code literally over a lunch break.
It sounds totally absurd, but it's not.
No, it's not a science fiction pitch anymore. It's a multi-billion-dollar reality that is, currently tearing through the global economy. And if you are listening to this deep dive right now, whether you manage a team or you write code or you're just trying to keep your inbox from exploding, this shift is coming for your daily routine.
It really is. I mean, it is the single most aggressive technological acceleration we've seen since the dawn of the internet. And what's truly staggering to me is just how quickly we've moved from theoretical research papers to actual deployed enterprise utility.
Which is exactly why we're doing this, because you, like everyone else, are probably drowning in the hype. You hear the buzzwords, large language models, foundation models, trillions of dollars, and it is incredibly easy to let your eyes glaze over.
Yeah, to just assume it's another Silicon Valley bubble.
Right, or something only the massive tech giants need to worry about. But our mission today is to cut through that noise entirely. So we are unpacking a highly comprehensive blueprint. It's titled A Practical Guide to Generative AI on AWS, Building, Deploying, and Securing Enterprise-Scale AI Applications.
It's a hefty title, but it's a vital document.
It really is.
Yeah.
And we're going to move from the microscopic, like the actual mathematical mechanics of how these models comprehend human language, all the way out to the macroeconomic impacts that are reshaping entire industries.
Yeah, because we really have to look at both ends of the spectrum. I mean, if you only look at the macroeconomic numbers, it just sounds like magic.
Right. Trillions of dollars.
Exactly. But if you only look at the math, it feels completely disconnected from human reality. So the goal here is to build a bridge between the silicon processing the data and the boardroom decisions governing that data.
Okay, let's unpack this because I am bringing my usual, healthy skepticism and an endless list of questions, and you are going to be our guide through the underlying architecture.
I'll do my best.
We need to connect the dots between these complex algorithms and the actual tangible future of your career. But before we get into server farms and trillion-dollar shifts, we really have to define our terms. Because the term AI is thrown around so casually now, it's basically lost our meaning.
Oh, completely. It's become a marketing term. Just a catch-all for any software that does something remotely clever.
Like my toaster has AI now.
Right, exactly. But mathematically and historically, it means something very specific. So to understand where we're going, we first have to understand the baseline of where we've been.
Well, the blueprint sets this up with a really clarifying comparison between biological perception and machine perception.
This is a great starting point.
Yeah, so if you think about human vision, the biological flow is pretty straightforward. You have the eye, which acts as the sensor. It takes in light, observes the physical world, and sends those signals to the biological brain.
Right, raw input to processing.
Exactly. The brain processes that visual perception, cross-references it with your memory, and then produces a cognitive reaction. So you look at a furry creature with 4 legs and a tail, and your brain instantly synthesizes those features and outputs the thought, that is a dog.
And for decades, the ultimate ambition of computer science was simply to replicate that specific biological flow electronically. We just wanted machines to be able to look at the world and categorize it the way like a toddler can.
And the mechanical equivalent to that biological flow is what we have traditionally called AI. Right? Instead of a human eye, you have a digital camera or a sensor capturing raw pixel data.
Yep, that's the input.
And instead of a biological brain, you pass that data into a deep neural network, and the cognitive outcome is the computer spitting out a categorical label. 99.8% probability this is a dog.
That is the defining characteristic of traditional or analytical artificial intelligence. It is fundamentally an engine of classification and prediction.
So it's basically reading what's already there.
Exactly. It processes what already exists. You feed it a training data set of 2 million pictures of dogs.
Mhm.
It mathematically maps the geometry of a snout, the distance between the eyes, the texture of the fur.
It learns the pattern.
Right. So when you hand it picture 2,000,001, it runs the math and predicts with high accuracy that this new cluster of pixels fits the established pattern.
So traditional AI is essentially the world's most sophisticated sorting machine. But the source points out a massive paradigm shift. And this is the threshold we have just violently crossed. We are moving from processing data to generating entirely new data.
This is the leap. This is what changes everything. Traditional AI says, I can look at this image and categorize it. Generative AI crosses the threshold into creation.
Okay, so how does it frame that?
It essentially says, I have analyzed millions of dogs, and I have learned the underlying conceptual representation of dogness. Therefore, using foundation models, I can generate an entirely original high-resolution image of a neon green dog wearing a spacesuit on Mars, rendered in the style of a 19th century oil painting.
Just wild.
It is. It is synthesizing novel text, images, and complex structural data that literally never existed in the universe before that specific prompt was run.
It's the difference between, like, a highly efficient filing clerk who can instantly find the exact document you ask for, and a novelist who can write you a brand new story on demand.
That's a perfect analogy.
But to really grasp how we got to the novelist, we need to look at this taxonomy visual in the source. I've been calling it the AI Russian nesting doll.
Oh, the concentric circles.
Yeah, it's a series of concentric circles showing how all these disciplines fit inside one another. And I think this is vital because people use terms like data science, machine learning, and generative AI completely interchangeably, and they represent vastly different layers of technology.
They absolutely do. Let's build the doll from the outside in, and let's use a tangible scenario so this doesn't get lost in abstraction.
Good idea.
Imagine you are running a massive global customer service center for an airline. The outermost circle, the biggest doll in the set, is big data.
Okay, big data, the buzzword of the 2010s.
Right. The blueprint defines this as managing volume, velocity, and variety. In our airline scenario, this is just the raw material. It's the millions of audio recordings of customer phone calls, the terabytes of text from live chats, the flight delay logs, the weather pattern.
Just a chaotic mess of information.
Exactly. It's the sheer chaotic mass of information. Big data is the architectural discipline of building the warehouse capable of holding and moving that information without collapsing.
But just having the audio file sitting on a hard drive doesn't do the airline any good, so we step one circle inward to data science.
Data science is the practice of extracting insights from that historical warehouse. And importantly, this is a human-driven process.
So humans are looking at the data.
Right. Your data scientists write queries to analyze the big data. They discover that on Tuesday mornings, when flights out of Chicago are delayed by weather, call volume spikes by 400% and the average hold time hits 50 minutes. They're finding statistical correlations in the past.
Okay, so that's data science. Then we step one circle deeper inside data science, and we hit artificial intelligence, the overarching field itself.
AI is the broad concept of machines mimicking human cognition. So in the airline call center, this might be a basic rules-based interactive voice response system.
Like when you call and it says, press 1 for booking?
A bit more advanced than that, but yeah. A customer calls in, and the system asks them to clearly say their flight number. The machine uses natural language processing to understand the spoken numbers and routes the call. It is doing something smart, but it is following a highly rigid, pre-programmed decision tree.
If they say this, do that.
Exactly.
Okay, then we step inside AI and we arrive at machine learning or ML.
This is where the methodology actually changes. With machine learning, you stop explicitly programming the computer with if-then rules.
You take away the decision tree.
Yes. Instead, you feed the computer data, and it learns the patterns autonomously. Going back to our call center, you don't write rules to tell the system what an angry customer sounds like.
That would be impossible to code anyway.
Right. How do you code angry voice? You can't. You feed an ML algorithm 10,000 audio clips labeled angry and 10,000 labeled calm. The algorithm figures out on its own that elevated volume, specific vocabulary, and a rapid cadence correlate with anger. It learns the pattern without you writing the explicit logic for it.
That makes sense. And inside machine learning, we have deep learning.
Deep learning is a highly specialized subset of machine learning that relies on multi-layered artificial neural networks.
Which are the ones inspired by the biological brain.
Exactly. They have layers of mathematical nodes that process data in complex, nonlinear ways. In our call center, deep learning is what allows the system to take a phone call with horrible static, a barking dog in the background, and a customer speaking with a heavy regional accent, and still accurately transcribe the speech into text in real time.
It handles the extreme complexity and noise.
Precisely.
And finally, inside deep learning, right at the very center, the tightest, most specialized circle is generative AI.
Generative AI utilizes those exact same incredibly complex multi-layered neural networks, but its specific purpose is radically different. As the source states, it relies on foundation models to create novel, human-like content.
So how does that apply to the airline?
Well, in our scenario, the generative AI system doesn't just route the angry call or transcribe it. It listens to the transcription, understands the context that the customer missed a connecting flight due to a baggage error, and instantly drafts a highly personalized, empathetic apology email.
Wow.
It even offers a specific voucher amount calculated to retain that specific customer's loyalty, all within milliseconds.
It is using the deep mathematical patterns not to sort, but to synthesize. But, and I have to stop you here, I need to push back, or at least admit a massive gap in my understanding.
Or what's missing?
Walking through that nesting doll makes logical sense, but it still feels like we just glossed over a profound mechanical leap.
Okay, how so?
Going from transcribing a voice to autonomously drafting a nuanced, empathetic apology email requires a level of contextual understanding that machines historically just did not possess. What physically changed in the computer science? How did we unlock this sudden ability to generate?
You are hitting on the fundamental limitation of the previous generation of AI. To understand the generative explosion, you cannot just look at the output. You really have to look inside the engine at the specific mathematical architecture that shattered the old limitations.
We are talking about the transformer.
We are talking about the transformer architecture. It was introduced by researchers in 2017, and it is the absolute bedrock of the current era.
Let's unpack the schematic the source provides on this. It's titled The Breakthrough, Transformer Architecture, and it sets up the problem by looking at the old way. Before 2017, the standard method for processing language relied on something called sequential processing.
Yes, RNNs or LSTM.
Right, recurrent neural networks.
Yeah.
And the blueprint has this massive red X through them. Why were they such a bottleneck?
Because they were forced to process information linearly, strictly sequentially, one word or token at a time.
One by one.
Yep. If you gave a recurrent neural network a long paragraph to translate, it would ingest the first word, update its internal state, then ingest the second word, update its state, and so on. It was a recursive step-by-step loop.
I've been thinking about an analogy for this. Tell me if this tracks. Relying on sequential processing is like trying to read a dense novel through a tiny keyhole carved in a piece of wood.
Oh, that's interesting.
You can only see one single word at a time. You look through the keyhole and see the, then you physically slide the book over. You see bank, you slide the book again. By the time you get to the end of a very long, complex sentence, you might have completely lost the context of the beginning.
Because you have no peripheral vision.
Exactly. You saw the word bank, but was it a financial institution or the muddy side of a river? Because you could only process the words in strict isolation in a linear timeline, you lose the broader, cohesive meaning.
That is a brilliant way to visualize it. RNN suffered from what we call the vanishing gradient problem. They had terrible memory for long sequences.
They just forgot what they read.
Basically, the further away a word was in a sentence, the less impact it had on the current word being processed. But the problem wasn't just linguistic, it was structural. Because sequential processing requires step 1 to finish before step 2 can begin, you cannot parallelize the work.
You can't split it up.
Right. You cannot take a sentence, break it into pieces, and hand it to thousands of computer chips to process simultaneously. You are trapped in a slow, linear bottleneck. They fundamentally lack the ability to achieve massive computational scale.
So the transformer architecture comes along and completely throws away the keyhole. It stops sliding the book. The transformer is like kicking the door open and instantly perceiving the entire page of text at the exact same moment.
Yes. The blueprint defines the magic element of the transformer as self-attention. This is the core mathematical breakthrough. Self-attention does not process left to right.
It looks at everything.
It dynamically weighs the context of every single word against every other word in a sequence simultaneously.
Simultaneously. That feels like the crux of everything.
It is. Think back to your bank example. I sat by the riverbank to eat my lunch. The self-attention mechanism looks at the entire array of words at once.
All at the same time.
Exactly. It looks at the word bank, and in the exact same computational cycle, it looks at river, sat, lunch, and I. It instantly calculates a mathematical relationship and a tension score between bank and river.
So it draws a line between them.
A very heavy, mathematically weighted line. It calculates a heavy weight between those two words, and the network essentially realizes, in this specific global context, bank is strongly associated with river. Therefore, it means the edge of a body of water, not a place with ATMs.
Mhm.
It grasps the full contextual tapestry all at once.
And because it operates entirely in parallel, taking the whole sequence at once, you are no longer waiting for step one to finish. You can throw 10,000 GPUs at a massive data set and process it in a fraction of the time.
The parallel processing is what unlocks the massive scale we see today.
But here's where it gets incredibly dense in the blueprint. The source takes us deeper inside this engine, breaking the transformer down into two distinct mechanical halves, the encoder and the decoder. It feels a bit like looking at the transmission and the engine block of a hypercar.
It's a very elegant machine when you break it down.
Let's start with the encoder. The visual flow here moves from input embeddings up to positional encoding, then into multi-head attention, and finally, a feed-forward network. What is the actual function of the encoder?
The encoder's primary function is deep comprehension. Its sole job is to ingest the input sequence, your prompt, your document, and distill it into a deeply nuanced, high-dimensional mathematical representation of context.
Okay, let's walk through those steps. The first layer, input embeddings. What is that?
It's translation. Machines do not understand the English language. They do not know what the word dog means. Embeddings translate human words into numbers.
Just random numbers.
No, specifically into vectors points in a highly complex mathematical space. In this space, words with similar meanings are plotted physically closer together.
So it turns vocabulary into geometry.
Exactly.
But wait, if we threw away the keyhole and we are reading the whole page simultaneously, didn't we just destroy the order of the words? I mean, in English, the dog bit the man and the man bit the dog use the exact same words, but the order dictates a radically different reality. If the machine processes them all at once, how does it know who is bleeding?
That is a great question, and it's exactly why the very next step is positional encoding. To compensate for the loss of linear order, this mechanism injects a tiny mathematical tag into each word's vector.
Like a timestamp.
Very much like a timestamp. It essentially tells the model, this word is a noun, it means this specific concept, and it appeared in the third position of the sequence. It restores the structural syntax.
Okay, that makes sense. Then it hits the multi-head attention layer.
Which is the self-attention we just discussed, but multiplied. It is called multi-head, because the network doesn't just do the attention calculation once. It runs multiple attention mechanisms in parallel.
Why does it need so many?
Well, one head might be looking specifically for grammatical relationships, like which verb connects to which noun. Another head might be looking for emotional tone. Another for historical context. It creates an incredibly dense web of relationships.
And then the feed-forward network.
It acts as a processing layer to solidify and stabilize all those complex mathematical relationships.
So by the time a sequence passes through the encoder, the machine has a mathematical understanding of that text that is arguably deeper and more comprehensive than a human reader.
It sees every possible syntactic and semantic connection, yes.
But comprehension is not creation. Reading a prompt perfectly does not generate an answer. That brings us to the second half, the decoder engine. The visual flow looks similar, but there is a massive twist at the bottom. It starts with something called masked multi-head attention, and the source explicitly notes this is hiding future tokens. Why are we suddenly blinding the machine?
Because the decoder's function is generation, and generation is fundamentally an act of prediction. The decoder generates the output sequence one token, one word or subword, at a time. Think about how you train a model to predict the future.
Okay.
If you give a model the sentence, "the cat sat on the mat," and you want to teach it to predict the word mat, you absolutely cannot let it see the word mat during the training process.
Right. That would be like giving a student the answer key during the exam. They wouldn't learn how to solve the math. They would just memorize the final number.
Precisely. Masked multi-head attention literally masks or obscures the subsequent words in the sequence. It forces the decoder to look only at the preceding context, "the cat sat on the alley," and combine that with the massive contextual comprehension handed over by the encoder.
So it takes what it knows so far and guesses.
The decoder takes that combined knowledge, runs it through its own multi-head attention and feed-forward networks, and mathematically calculates the most probable next word. It guesses Matt.
And then what?
Then it takes Matt, adds it to the sequence, and predicts the next word. It is an autoregressive loop of creation.
It is stunning when you break it down like that. But what is truly fascinating for anyone actually trying to deploy this technology is that you do not always need both engines running at the same time.
Right. You don't always need the whole hypercar engine.
The blueprint includes a transformer architecture's comparison matrix, which is basically a cheat sheet for building enterprise AI. It breaks the models down into 3 distinct columns: encoder only, decoder only, and encoder-decoder.
They are completely different tools for different mathematical jobs.
Let's walk through these, because if a business chooses the wrong architecture, they're essentially using a hammer to turn a screw. Let's start with the first column, encoder-only models. The blueprint describes their mechanic as bidirectional context via masked language modeling. We know the encoder is the comprehension engine.
Yes, and bidirectional means it looks to the left and to the right of a given word simultaneously to fully grasp its meaning within the whole block of text.
So, if it is purely a comprehension engine, what is the actual business use case?
It is unparalleled for analyzing existing text. The source lists text classification, entity recognition, and sentiment analysis.
Give me an example of that in the real world.
Say you are a financial institution and you have 10,000 pages of dense regulatory updates. You need a system to scan those pages, extract every single mention of a new tax law, and classify the overall regulatory tone as restrictive or lenient. You deploy an encoder-only model.
Because you don't need it to write a poem.
Exactly. You do not need it to create. You need it to comprehend deeply. The classic, highly influential example provided in the blueprint is BERT, developed by Google.
Okay, next column, decoder-only models. The mechanic listed here is unidirectional context via causal language modeling. Unidirectional meaning it only looks backward at what has already been written to predict the next token.
This is the superstar architecture of the current generative wave. This is the engine behind ChatGPT, Anthropic's Claude, and Meta's Llama.
This is the novelist.
Yes. Because it is purely, obsessively focused on predicting the most logical next word based on the previous sequence, it is unmatched at pure creation. The blueprint explicitly states it is best for text generation, conversational AI, and code generation.
So if you want a chatbot to dynamically converse with a customer or an assistant to write a Python script from scratch, you need a decoder-only model.
That's right.
And finally, the hybrid column, encoder-decoder models. This utilizes both the comprehension engine and the generation engine. The primary mechanic listed here is span corruption and autoregressive reconstruction.
Okay, we need to ELI 5 this.
Explain like I'm 5.
Yeah, explain this to me like I'm a 5-year-old, because span corruptions sounds like a bridge collapsing. What does that actually mean in the context of training a model?
Let's use a very physical analogy. Imagine I hand you a beautifully written, complex ransom note. But before I hand it to you, I take a pair of scissors and I literally cut out random chunks of the text.
Just snip them out. Not just single words, but entire spans of words. Phrases. We have the blank. Leave the money at the blank by midnight. That is span corruption.
Okay, you've corrupted the data.
Right. Now, your job as the AI is to reconstruct that note perfectly. To do that, you first need the encoder engine to deeply comprehend the surviving context of the note, the tone, the grammatical structure, the remaining vocabulary.
It figures out it's a ransom note, not a grocery list.
Exactly. Once the encoder grasps the deep context, it hands that understanding over to the decoder engine. The decoder then autoregressively generates the missing stands of text to rebuild the original document.
That's a great way to train it.
By training a model this way, forcing it to rebuild corrupted information, you create a system that is incredibly powerful at transforming one complex sequence into another complex sequence.
So that perfectly explains the use cases listed here. It says encoder-decoder models are best for translation, summarization, and sequence-to-sequence tasks. Like, if I feed it a 50-page legal contract in English and I want a tight 2-page executive summary generated in fluent French, I need the encoder to fully grasp the massive English context and the decoder to generate the precise French output. Examples here are T5 and BART.
Exactly. When an enterprise architect is designing a system, they're not just vaguely saying, we need generative AI. They were looking at this precise matrix. They're defining the specific business friction point, and then selecting the structural engine mathematically designed to resolve it.
Which is the perfect transition into the reality of deploying this. Because knowing how the transformer engine works is intellectually fascinating, but how does an enterprise actually build and run this without collapsing under the sheer computational weight?
That's the real challenge.
We are talking about models with hundreds of billions of parameters doing massive matrix multiplications. You cannot run this on a corporate laptop. This brings us to segment 3 of the blueprint, the AWS Generative AI stack.
This is where we leave the theoretical math and hit the cold, hard metal.
The blueprint introduces a very specific enterprise philosophy right up front. It emphasizes a multi-layered ecosystem explicitly designed for security, massive scale, and flexible model choice. And it boldly states that it is rejecting the one-size-fits-all black box approach. Why is that rejection so critical for a business? Because honestly, a black box sounds really easy. Just send the data away and get an answer back.
A black box is easy, but it is an unacceptable risk for a serious enterprise.
Why?
Let's say you are a global healthcare provider. You have highly sensitive patient records, proprietary drug research, and strict IPAI compliance regulations. If you use a black box AI provider, meaning you just ping a third-party API over the internet, you have zero visibility into what happens to your data once it leaves your walls.
It's just out there.
You don't know what hardware it is running on, what security protocols are active, or most critically, whether your highly proprietary data is secretly being used to train that provider's future models. You surrender control.
Which is terrifying for a Fortune 500 company.
The AWS philosophy is built on the premise that enterprises require granular visibility and control at every single layer of the stack.
So let's build that stack layer by layer, starting from the bedrock. Layer 1, infrastructure and training. The hardware and the orchestration. The blueprint gets right down to the actual silicon chips. It details purpose-built AWS Trainium and Inferentia chips paired with NVIDIA GPUs and something called EC2 capacity blocks.
The silicon is everything right now.
I want to talk about the physical reality of this for a second because the sheer infrastructure required is mind-bending.
The physical reality is that generative AI is currently bottlenecked by the global supply of specialized silicon. Training a foundation model from scratch requires orchestrating tens of thousands of GPUs running continuously for months, consuming massive amounts of electricity.
It's an industrial operation.
AWS recognized this hardware bottleneck and began designing custom silicon years ago. Trainium is a chip designed explicitly at the microscopic level to accelerate the specific math required to train deep learning models.
And Inferentia.
Inferentia is designed for the deployment phase, when the model is actually running and generating answers, which requires a different type of computational efficiency.
So they are building bespoke hardware just to drive down the cost and increase the speed of these specific AI workloads. And the EC2 capacity blocks, what are those?
Well, because high-powered GPU compute is so scarce globally, enterprises face a nightmare of scheduling. Capacity blocks allow an enterprise to essentially reserve a massive cluster of this hyper-specialized hardware for a specific duration. You lock in the power you need exactly when your data scientists are ready to run their training cycles. It guarantees access to the silicon.
But raw, brute force computing power is useless without a way to control it. That is where the software orchestration comes in at layer 1. The blueprint highlights a platform called Amazon SageMaker AI. It describes it as a fully managed hub for distributed model training, hyperparameter tuning, and seamless MLOps deployment.
SageMaker is the conductor of the orchestra.
Let's pause on hyperparameter tuning, because that is another piece of dense jargon. If the model is learning the parameters from the data on its own, what is a hyperparameter? Let's ELI 5 this one too.
Think of training an AI model like baking an incredibly complex multi-tiered cake. The data, your text, your images are the raw ingredients. The neural network architecture is the oven.
Okay, ingredients and oven.
The parameters are the actual chemical reactions happening inside the cake as it bakes. The model learns these on its own. But the hyperparameters are the external knobs on the oven. It is the temperature setting. It is the exact baking time.
Oh, I see.
In AI, hyperparameters are things like the learning rate, how aggressively the model should update its assumptions after seeing new data, or the batch size, how many examples it should process at once.
So if you set the temperature too high, if the learning rate is too aggressive, the outside of the cake burns, but the inside is raw. The model overfits and becomes erratic.
Exactly. And if the temperature is too low, it takes a month to bake the cake and you waste millions of dollars in compute time. Hyperparameter tuning is the highly complex, iterative process of finding the absolute perfect settings on those external knobs so the model learns efficiently and accurately. SageMaker provides the environment for data scientists to automate that tuning across massive clusters of GPUs simultaneously.
The source also mentions a feature within SageMaker called Jumpstart.
Jumpstart is essentially an accelerator. Training a massive model from absolute zero is incredibly expensive and time-consuming. Jumpstart provides a curated hub of pre-trained open-source foundation models.
So you don't start from scratch.
Right.
Go.
It allows a business to say, we don't need to invent the wheel. Let's grab this highly capable open-source model, pull it into our secure SageMaker environment, and immediately start fine-tuning it on our specific data. It dramatically shortens the runway from concept to deployment.
Okay, so layer 1 is the heavy lifting, the silicon and the orchestration. Now we move up the stack to layer 2, which honestly, as I read through this blueprint, feels like the nerve center. Amazon Bedrock, the builder's hub.
Bedrock is huge.
If layer 1 is the engine room of a submarine, layer 2 is the command bridge. The blueprint breaks Bedrock down into 4 primary prongs. Let's explore these, because this is where the enterprise strategy really takes shape. The first prong is flexible model choice.
Model choice is critical.
Bedrock provides single API access to a roster of industry-leading models. Anthropic's Claude, Meta's Llama, Mistral, and Amazon's own Titan family. My question is, why does a company need that much variety? If Claude 3 is supposedly the smartest model, why not just use that for everything?
Because in enterprise architecture, using the smartest, most massive model for every single task is economically ruinous. It is like using a Lamborghini to deliver a single pizza.
That's an expensive delivery.
Right. These models have vastly different cost structures, latency speeds, and areas of expertise. A massive, complex model like Claude might be required for synthesizing complex legal briefs or writing dense software code. But if you just need a model to quickly summarize a string of customer service emails, you want a smaller, lighter, incredibly fast open-source model like Llama 3.
So Bedrock lets you switch between them.
Bedrock allows an architect to route different tasks to different models seamlessly through one single interface, optimizing for both performance and cost. Furthermore, the technology is moving so fast that today's cutting-edge model will be obsolete in 6 months. Bedrock ensures you are never locked into a single provider's lifecycle.
That makes total sense. Optimize the tool for the task. The second prong of Bedrock is customization. The source mentions traditional fine-tuning, but it spends a massive amount of real estate emphasizing something called RAG, Retrieval Augmented Generation.
RAG is everything right now.
It defines this as the mechanism to securely anchor models to proprietary corporate data. We really need to dig into RAG, because reading between the lines, this seems like the actual holy grail for corporate AI adoption.
It is the holy grail because it solves the fundamental flaw of generative models. Here is the problem. A foundation model only knows the information it was trained on, up to a specific cutoff date.
Like it read the whole internet, but only until last year.
Exactly. It knows everything on the public internet as of, say, last year. What it absolutely does not know is your company's Q3 revenue projections, or your updated HR policies, or the specific technical specs of a product you haven't released yet.
It's blind to your internal stuff.
Right. Therefore, if an employee asks a generic AI a question about internal corporate strategy, the model will hallucinate. It will confidently fabricate an answer because it is designed to generate text, not to admit ignorance.
It wants to finish the sequence, even if it has to invent the facts.
Precisely. RAG Retrieval Augmented Generation is the architectural solution to hallucination. When a user queries a RAG system, the system pauses. Before it ever talks to the generative AI model, it takes the user's query and searches your secure internal corporate databases.
Like an internal Google search.
Yes. It retrieves the highly specific, factual documents relevant to the question. It then packages the user's original question along with the retrieved factual documents and sends that entire bundle to the foundation model with a strict instruction. Answer this question, but you may only use the information provided in these specific attached documents.
So it forces the AI to essentially take an open book test, and you are handing it the exact textbook.
Exactly. It anchors the immense reasoning and formatting capabilities of the AI strictly to your verified proprietary data. It drastically reduces hallucinations, provides accurate citations, and makes the AI immediately practically useful for the business.
That is a game changer. The third prong of Bedrock is agents. The source defines this as the dynamic orchestration of multi-step tasks across enterprise systems.
This is where AI evolves from a passive conversationalist to an active worker.
Okay, so.
A standard chatbot just generates text. An agent is granted permission to take action. An agent is integrated into your corporate APIs, your billing software, your inventory management, your CRM.
Give me a tangible example.
Let's say you tell an agent, onboard the new software engineer starting on Monday. The agent dynamically breaks that prompt down into a sequence of tasks. It autonomously interfaces with the HR software to generate a profile. It interacts with the IT ticketing system to order a laptop. It drafts the welcome email and schedules the orientation meetings.
It's just doing all of that on its own.
Yes, it navigates across different software platforms, executing a multi-step workflow autonomously.
It's moving from generating words to generating actions, which naturally brings us to the fourth prong of Bedrock, and honestly the one I'm most skeptical about, guardrails.
Necessary buzzkill.
The blueprint defines these as customizable safeguards for PII redaction, content filtering, and responsible AI deployment. I need to push back on this. If we are giving AI systems the power to read proprietary data via ARI and execute actions across corporate systems via agents, the security risk seems catastrophic.
It's a huge risk if not handled correctly.
And regarding content filtering, if we are constantly filtering out off-brand topics or restricting the model, aren't we basically lobotomizing the reasoning capabilities of the AI? How does an enterprise actually balance keeping the system safe without making it useless?
That tension between capability and safety is the central tightrope walk of enterprise AI. And your fear regarding the security risk of agents is entirely justified. That is exactly why guardrails and Bedrock are not an afterthought or a gentle suggestion. They are a hard architectural layer that sits directly between the user, the foundation model, and the data.
How does it actually work mechanically?
You as the enterprise define explicit policies. Let's look at PII, personally identifiable information. You can configure a guardrail that utilizes pattern recognition to scan every single prompt going in and every single response coming out.
Scanning everything.
Yes, if it detects a string of numbers that mathematically resembles a social security number, a credit card, or a patient ID, it instantly redacts it or blocks the transaction entirely before the data ever leaves the secure environment. It is an automated high-speed sensor.
Okay, that protects the data, but what about the lobotomizing aspect? If a bank sets a guardrail that says never offer investment advice, does that make the AI stupid?
It doesn't make it stupid. It makes it compliant. A bank cannot afford the liability of an AI hallucinating a stock recommendation. The guardrail intercepts the prompt. If a customer types, "What stocks should I buy?" the guardrail categorizes the intent as investment advice, blocks the prompt from reaching the generative model, and instead returns a pre-approved, legally vetted response.
So the AI never even sees the question.
Right. And here's the key to balancing safety and utility. Guardrails are integrated with your existing identity systems. When used with RAG, the AI inherits the user's permissions.
Explain that.
If a junior analyst asks the AI for the Q4 payroll data, the system checks their ID, realizes they don't have clearance for payroll, and denies the retrieval. The AI can only see the data that the specific human asking the question is already legally authorized to see.
It acts like a highly intelligent bouncer at the door of the data warehouse. Okay, so layer 1 is the silicon engine. Layer 2, Bedrock, is the control bridge. That brings us to segment 4 of the blueprint. Applications, economic potential, and high-value use cases. Layer 3 of the stack is enterprise applications.
This is where it gets real for the employees.
This is the layer the actual end user interacts with, and the primary application highlighted is Amazon Q.
Amazon Q is the culmination of the entire stack. It takes the infrastructure, the foundation models, RAG architecture, and the guardrails, and packages them into a direct, out-of-the-box product. The blueprint divides it into two main personas, Q business and Q developer.
Let's start with Q business. The slide describes it as a generative AI assistant that connects securely to over 40 enterprise data connectors to synthesize internal corporate data.
Q Business is essentially your enterprise's omniscient assistant. It connects directly to your Microsoft SharePoint, your Google Drive, your internal wikis, your Slack channels. It ingests all of that unstructured data.
So it reads everything you plug it into.
Exactly. Instead of an employee wasting 3 hours digging through 6 different portals trying to find the updated travel expense policy for Europe, they just open a chat window and ask Q. Q uses the RAG architecture we talked about to instantly retrieve the correct updated documents, synthesizes a clear answer, and provides direct hyperlinks back to the source material.
It eliminates the immense friction of corporate knowledge discovery.
Completely.
And then there is Amazon Q Developer. The blueprint calls this a powerful IDE companion. IDE being integrated development environment, the software where coders actually write and test code. I am marveling at the specific capabilities listed here: real-time code suggestions, autonomous debugging, and automated complex workflows. And the primary example they highlight is seamless legacy Java upgrades.
We touched on this in the very beginning.
Yes, the intro hook.
Hmm.
But why is upgrading old Java code such a vital, high-value example?
Because technical debt is choking massive enterprises.
Yeah.
You have global financial institutions and government agencies running absolutely critical infrastructure on older, deprecated versions of Java.
And that's dangerous.
Those older versions become massive security liabilities. But upgrading that code to the latest version is a nightmare. It is tedious, manual, line-by-line drudgery. It requires mapping hundreds of dependencies, and human engineers absolutely despise doing it because it is prone to error and incredibly boring.
It is the definition of routine, non-strategic activity.
Exactly. QDeveloper functions as an autonomous agent in this scenario. You point it at a sprawling repository of legacy code. It analyzes the entire architecture, comprehends the dependencies using the deep context we discussed earlier, and autonomously rewrites and modernizes the codebase.
It just writes the new code.
It does, and then it presents it to the human engineer for final review. It compresses a migration project that would traditionally take a team of senior engineers 6 agonizing months into an automated workflow that can be completed in weeks or even days.
Which perfectly sets up the staggering economic numbers presented in the source. This is the trillion-dollar potential slide. The blueprint features a massive typography callout. Generative AI presents a $2.6 trillion to $4.4 trillion potential annual addition to the global economy.
We really need to let the sheer scale of that number sink in. That is not total revenue shifting hands. That is net new, additional value injected into the global economy every single year.
It's hard to even picture that.
It is the economic equivalent of spontaneously birthing a new country the size of the United Kingdom and adding its entire GDP to the world.
But how? How are we physically manifesting trillions of dollars out of thin air? The source answers that question with a concept it calls the productivity shift. It states that generative AI has the capability to automate 60% to 70% of current routine employee activities.
This is the fundamental economic engine of the entire revolution. It is about the reallocation of human capital.
Explain that.
Think about the engineer manually rewriting Java or the HR rep spending hours collating data for a report. That is routine work. It is necessary, but it does not generate new value. By automating 60% to 70% of that daily drudgery, you are fundamentally shifting the workforce.
So you aren't firing people.
You aren't necessarily replacing the human worker. No. You are freeing up the vast majority of their time, allowing them to redirect that energy toward tasks that currently only humans can do: complex strategic planning, profound empathy, nuanced problem solving, and relationship building. You are elevating the human workforce from operators to directors.
To visualize where this shift will happen, the blueprint provides a value heat map. It claims that 75% of this multi-trillion-dollar value is concentrated in just 4 primary business functions: marketing and sales, customer operations, software engineering, and R&D. Why is the value so heavily skewed toward those 4 areas?
Because those 4 specific domains are entirely dependent on the exact capabilities that generative AI excels at. Marketing and sales run on content generation and personalization. Customer operations run on synthesizing information and communicating empathy.
Okay, and software.
Software engineering runs on writing and debugging complex structural logic. And R&D runs on analyzing massive data sets to predict new outcomes. Generative AI mathematically aligns perfectly with the friction points of those departments.
Let's ground this massive macroeconomic theory in tangible reality. The blueprint walks through 3 specific high-value industry impacts. Let's look at the first one: banking. A projected $200 to $340 billion annual impact.
A huge sector for AI.
The specific use cases listed are automated legacy code conversion, which we just discussed with QDeveloper generative risk model documentation, and hyper-customized retail banking offers. What's the deal with risk model documentation?
The risk model documentation is a massive, hidden sinkhole of human capital for banks. Regulatory bodies require banks to maintain incredibly complex mathematical models to assess risk. Every time a model is tweaked, a human has to write hundreds of pages of highly technical, legally binding documentation explaining the change. It is grueling work.
And Gen AI can just do it.
Generative AI can ingest the mathematical changes to the risk model, comprehend the logic, and automatically draft the comprehensive compliance documentation, saving millions of dollars in human hours while actually reducing the risk of human error in the paperwork.
Wow. And the custom offers.
Meanwhile, the hyper-customized offers represent a shift in revenue generation. Instead of a bank segmenting its millions of customers into three broad buckets and sending them generic credit card offers, generative AI analyzes the granular transaction history of an individual.
So it looks at exactly what I buy.
Yes, and it generates a highly specific, personalized financial product tailored exactly to their current life circumstances, massively increasing conversion rates.
The second industry highlighted is retail and CPG consumer packaged goods. This represents the largest slice of the pie on the slide, a $400 to $660 billion impact. The use cases include dynamic marketing copy generation, augmented reality customer support, and accelerated consumer research via something called synthetic customers.
This is a wild concept.
I want to pause heavily on synthetic customers because when I read this, my mind was blown. My analogy for this is that it is like having an infinite, instantaneous focus group that never gets tired and never asks for a gift card. Tell me I am understanding this correctly.
Your analogy is spot on. Historically, if a major CPG company wants to launch a radically new flavor of a sports drink, they have to spend months and millions of dollars running physical focus groups. They hire people, put them in a room, ask them questions, and try to extrapolate those answers to the broader population.
And it's probably pretty biased based on who showed up.
It is slow, expensive, and often inaccurate. With generative AI, a company can create synthetic customers. These are highly complex digital personas powered by large language models that have been rigorously fine-tuned on massive amounts of demographic, behavioral, and purchasing data.
So you basically create a digital clone of like a suburban millennial who exercises 3 times a week and prefers organic ingredients.
Exactly. And you don't just create one, you generate 10,000 unique variations of that persona. Then you present your new product concept, the proposed pricing, and the marketing copy to these synthetic personas.
And they react to it.
The models instantly generate feedback, debate the price point, critique the packaging colors, and simulate purchasing decisions based on their programmed behavioral traits. You can run a massive, highly detailed focus group in a matter of hours, radically accelerating the R&D feedback loop and drastically reducing the risk of a product flop.
That is both incredible and slightly terrifying. The third industry is pharma and healthcare, a projected $60 to $110 billion impact. The use cases include automated patient documentation, medical scan analysis, and accelerated drug discovery, with a specific, highly technical note on protein folding predictions.
This is the domain where generative AI shifts from maximizing corporate revenue to fundamentally altering human longevity.
How does it help with drug discovery?
The process of discovering a novel, life-saving drug historically involves years of agonizing trial and error in a physical laboratory. Scientists try to figure out how incredibly complex protein molecules fold in three-dimensional space and how they interact with diseases. It is a biological puzzle of almost infinite complexity.
And AI solves the puzzle.
Generative models, utilizing the exact same transformer architecture we discussed earlier, the ability to look at a massive sequence and understand the mathematical relationships of every part simultaneously, can predict the three-dimensional structures of proteins from their base amino acid sequences with astonishing, unprecedented accuracy. It takes the drug discovery phase from years of physical experimentation down to days of computational simulation.
And on the ground level, in the clinic, the automated patient documentation is a massive quality of life shift. An AI system securely listens to a complex doctor-patient interaction, comprehends the medical terminology, and instantly generates the structured clinical notes for the electronic health record.
It frees the physician from being a data entry clerk, allowing them to actually look the patient in the eye.
It all circles back to that central thesis, the productivity shift, reallocating human capital to where it matters most. Which brings us to the final crucial segment of our deep dive. We have explored the underlying engine, we have built the infrastructure stack, and we see the multi-trillion-dollar economic reality on the horizon. The final practical question for any leader listening is, how do organizations actually move from an exciting idea to actual secure deployment without failing spectacularly?
Because the graveyard of enterprise technology is full of brilliant ideas that failed in execution.
The blueprint outlines the enterprise advantage, specifically making the case for why organizations are choosing to build on AWS. It breaks down 6 core pillars. Let's run through these, and I want you to maintain an objective distance here. What are the actual benefits, and what are the trade-offs? Pillar 1, elasticity and scale. The blueprint promises auto-scaling infrastructure that absorbs massive peak workloads seamlessly.
The reality of generative AI workloads is that they are incredibly spiky and unpredictable.
Spiky? Like up and down.
Yeah. A company might need massive, concentrated computational power to fine-tune a model for 3 days and then need almost none for a week. Or an AI-powered retail app might experience a 10,000% surge in traffic during a holiday sale. If an enterprise tries to build this infrastructure on-premise, buying their own physical servers, they have to buy enough hardware to cover their absolute maximum possible peak, meaning those expensive servers sit idle 90% of the time.
Which is a waste of money.
The cloud provides elasticity, the infrastructure agrees with your demand, and you only pay for the precise compute cycles you consume.
Pillar 2 is cost efficiency, which ties directly into the pay-as-you-go pricing for intensive GPU workloads. Pillar 3 is managed services, reducing operational overhead through platforms like Bedrock and SageMaker. What's the catch there?
The trade-off here is control versus velocity. If you build everything from scratch yourself, you have absolute control over every single line of code. But you also have to hire a massive army of highly specialized, incredibly expensive infrastructure engineers just to keep the servers from crashing.
And managed services solves that.
Managed services abstract away the plumbing. It allows an enterprise to focus its limited engineering talent on building the actual application that serves their customers, rather than managing the database clusters.
Pillar 4, global reach, deploying AI at the edge globally for ultra-low latency. Pillar 5, unmatched choice, the promise of zero vendor lock-in. Now, I have to look at this with a critical eye. AWS claims unmatched choice through Bedrock, allowing you to use Anthropic, Meta, or Amazon models. But if you build your entire ARIG architecture, your databases, and your security protocols strictly within the AWS ecosystem, aren't you still fundamentally locked into AWS as a vendor, even if you can swap the specific AI model?
That is very astute, critical observation. You are correct. The zero vendor lock-in claim specifically refers to the foundation models themselves.
Not the infrastructure.
Right. In the past, if you built an application on a proprietary API, you were permanently tied to that specific company's AI research. Bedrock frees you from model lock-in. However, you are absolutely integrating deeply into the AWS cloud ecosystem. The enterprise architecture, the IAM security roles, the data storage formats, the SageMaker pipelines creates a massive center of gravity. Migrating that entire infrastructure to a different cloud provider later would be a significant undertaking.
Why I do it?
Enterprises choose this path because the immediate velocity, security, and integration benefits of a unified ecosystem currently far outweigh the theoretical future risk of platform lock-in.
That is the pragmatic reality. And that brings us to Pillar 6, which you have hammered home repeatedly today. Security and governance. Enterprise-grade IAM, encryption, and strict data privacy. Let's ELI5 the IAM part. Identity and access management. Why is this so crucial for generative AI?
Think of IAM as the most sophisticated, omnipresent bouncer at the most exclusive club in the world. But instead of just checking your ID at the front door, this bouncer follows you inside and checks your ID. Before you're allowed to open every single door, look at every single piece of paper, or speak to any specific employee.
Okay, that's intense.
In a generative AI context, especially with RAG, the AI system is immensely powerful. It can read everything. IAM ensures that the AI assumes the identity of the user asking the question. If you don't have the IAM cryptographic keys to view the Q3 financials, the AI cannot retrieve them for you, period.
And the blueprint specifically highlights this final crucial detail in parentheses. Your data is not used to train base models.
I will reiterate this because it is the absolute line in the sand for corporate adoption. When an enterprise utilizes Amazon Bedrock, the proprietary corporate data, the highly sensitive documents retrieved using RAG, the specific prompts your employees type into Amazon Q is cryptographically isolated.
So no one else learns from it.
It is strictly guaranteed that neither AWS, nor Anthropic, nor Meta can access that data to train their underlying base models. Your competitive advantage remains entirely yours. Without that ironclad contractual and mathematical guarantee, none of these massive enterprise use cases are viable.
So, assuming the security is locked down, how do we actually build the project? The source provides an incredibly clarifying visual titled the Gen AI Project Lifecycle. And importantly, it is not a straight linear timeline. It is visualized as a hexagonal loop, almost like a star, indicating continuous iterative motion. It starts with define use cases, then it immediately moves to establish data strategy.
And that second step is where 80% of generative AI projects currently fail.
Really?
Yeah.
Why?
Executives get blinded by the hype. They buy the fancy AI models first and try to figure out their data architecture second. It is like buying a Ferrari engine and trying to drop it into a rusted-out chassis. You must establish a clean, secure, unified data strategy first. Your data must be organized, digitized, and accessible before you can effectively utilize RDAG or train any models. The AI is only as intelligent as the data foundation it sits upon. Once the data is clean, the loop moves to select foundation models, using Bedrock to find the right architectural tool for the specific job, then evaluate and interpret, rigorously testing the outputs for accuracy and bias, then deploy application, and finally monitor and iterate, which feeds right back into defining new use cases. And the blueprint shows this continuous spinning loop supported by three massive central pillars: process, people, and technology. These three pillars are the stabilizers that keep the loop from spinning out of control. Process means establishing rigorous automated MLOps workflows so that deploying a model is repeatable and safe. Technology means utilizing the scalable infrastructure we discussed.
And people.
People is arguably the most difficult and most important pillar. You cannot just deploy an advanced agent like Amazon Q across your company and walk away. You have to actively, continuously upskill your workforce. You have to train your employees on how to effectively prompt the AI, how to critically evaluate its outputs, and most profoundly, how to shift their own mental frameworks from "I am the person doing the task" to "I am the manager directing the intelligence that does that task."
Which perfectly brings us to the final synthesis slide in the blueprint, the path forward. The core insight here summarizes everything we have unpacked over the last hour. Generative AI has officially crossed the threshold from an esoteric research experiment into vital enterprise utility. By pairing the revolutionary parallel processing of the transformer architecture with the highly secure, scalable infrastructure of the AWS stack, organizations are moving rapidly from conceptual proofs to live production. And the final visual provided is an exponential growth curve. It is a chart showing return on investment shooting dramatically upward from Q1 to Q4.
It is illustrating the compounding, nonlinear value of this technology. It is a flywheel effect.
How does the flywheel spin?
When you successfully automate routine tasks, you increase your organizational speed. When you increase your speed, you free up capital to deploy more complex models. When you deploy more models, your employees uncover entirely new, unexpected use cases. The return on investment compounds rapidly, but it can only achieve that exponential curve if the underlying infrastructure is fundamentally designed to scale securely without fracturing.
We have covered a truly massive amount of ground today. From the historical bottleneck of sequential processing and the mathematical elegance of the transformer, all the way to the multi-trillion-dollar macroeconomic impacts reshaping banking, retail, and medicine. And the source material leaves us with one final definitive takeaway, which I think is the ultimate synthesis of this entire blueprint. The competitive advantage belongs to those who build secure data foundations today to power the foundation models of tomorrow.
It's a stark call to action for leadership. The foundation models themselves are going to continually evolve. The transformer architecture might be superseded by something even more powerful in 5 years. But the foundation of secure, high-quality, meticulously organized proprietary corporate data is a permanent, appreciating asset. If an enterprise builds that data foundation and that security infrastructure right now, they are perfectly positioned to leverage whatever incredible capability the AI industry produces next.
Thank you for being our guide through this incredibly dense architecture. It truly helps to cut through the relentless hype and examine the actual mathematical mechanics and the hard economic realities driving this revolution. And to you, listening to this, thank you for taking the time to join us on this deep dive. But before we sign off, I want to leave you with a final provocative thought circling all the way back to that staggering productivity shift statistic. It is a question I have been continually pondering ever since I first read this blueprint, and it applies directly to your life. If generative AI truly has the capability to cleanly automate 60% to 70% of your current routine daily activities, what does the strategic work of your future actually look like? Are you genuinely prepared for a professional world where your primary value is no longer in executing the task, but in directing the intelligence that does?